we talked about how we have to abandon the notion of particle. So for the remainder of this course, we're not going to be motivated by particles. We let go of particles. We replace it by the notion of field. And then at some point, we come back and say, define particles again. Particles are going to be emergent. We gave examples of quasi-particles, right? So we have to, within the framework of quantum field or field theory, we'll have to define particles. But for now, we just let go. Then we worked out in lecture 3. We worked out an example of the simplest example of quantum field theory, which was the theory of quantum sound phonons. We saw that in low energy, it had these emergent degrees of freedom, quasi-particles, phonons, that were actually relativistic in that case. So it was an example, it was a nice example where you saw how the UV degrees of freedom were very different compared to the low energy degrees of freedom. In terms of their statistics, hopefully that's clear, right? The UV degrees of freedom were distinguishable. The low energy degrees of freedom were indistinguishable and bosonic. Anyway, then last lecture, we start section 2 or chapter 2. We started talking about locality. We named 3 principles for field theory: locality, symmetry, the one that I always forget, positivity of energy, right? So at some point, maybe in this course, maybe QFT2, we're going to get to the axioms of quantum field theory. But then you'll see basically those are going to be repeated in a very formal language. But for now, the section of the course is about locality. We're going to go through it in the context of classical physics to make it clear. There are aspects of locality that are quantum. We'll get there when we get there, right? There's already some stuff to learn about locality here. Yes, last lecture, we started the discussion of locality, and then we said that it's clearest in the action formulation of classical mechanics. So it's what you could write down classical mechanics as an action principle. The extrema of the action are the path that classical particles take or classical fields take, as we see today. So in the case of particles, action was a function. And then in the case, well, actually, even in the case of +1 dimension, it becomes a functional. But action in quantum field theory, in field theory, is a functional, meaning there's a map from C infinity. C infinity means smooth, infinitely differentiable functions. Infinitely differentiable functions, smooth functions of R1, comma D, Minkowski space, to real numbers. And we said, I just maybe in passing, I mentioned that we want the action to be real. That's important for us. So these are field configurations, right? Locality was reflected in the fact that the action is a single integral over space-time of a density that we call Lagrangian density. That is a manifestation of locality, right? We talked about the connection between this and the Hamiltonian picture. We derived the equations of motion in the case of classical physics, where you could, in terms of, which was a 0 + 1 dimensional field theory. Today, we're going to repeat that as the first slide, after this, like in the next slide, and derive the equations of motion, basically the Euler-Lagrange equations for classical fields. And this is what I was hoping to finish last time. All right, so we're going to do that. What else are we going to discuss? Today, we're going to discuss 4 examples. To make the discussion less abstract, we're going to discuss 4 examples of field theories. We're going to see the manifestations of locality and various aspects of it. First one is massive relativistic free scalar fields. Okay, massive relativistic free scalar fields. So you should already know what these terms involve. Maybe you don't know yet, but scalar and massive tell you what the representation is under Poincare transformations. So our representation, we're going to get there, we're going to discuss it. When we talk about representation theory, we're going to label them by labels, quantum numbers. And representations of Poincare are going to be labeled by mass, m², and spin, right? Turns out that scalar is a spin 0, blah, blah, blah. So relativistic is relativistic, you know what it means. And free means Gaussian. So the action is going to be second order, right? It's going to be Gaussian. Then the example 2 is going to be non-relativistic free boson field. I have a point to make in example 2. I will not have time to elaborate on this extensively, but I want you to see a connection between classical physics and quantum physics. So that's, we're going to go through that. It will be a connection between classical equations or equations of motion of classical fields and Schrodinger equation. That's what we're going to talk about over there. We're going to go through Maxwell theory as a first example of as an example of a non-local theory, right? So it's a theory that is non-local, but has a very, very peculiar form of non-locality. And we're going to discuss that. Of course, we're going to stick to this fundamental principle of locality. That's why we're going to introduce some redundant degrees of freedom called gauge degrees of freedom. And then we're going to talk about statistical field theory as the last example. I probably will run out of time. I'll just wrap it up pretty quickly, but just so that you guys have seen these examples. All classical physics, right? Any questions about the structure where we're going today? All right. So what I'm gonna do first is I'm gonna repeat I'm gonna derive the Euler-Lagrange equations of motion. EOM is equations of motion in field theory. So the analogy to keep in mind, previously we talked about a particle going from Ti to Tf, and the field in that case was 0 + 1 dimensional. It was Qi of T, right? I are the numbers, right? And then this was T of I, T of F. Keep these fixed, and there are all sorts of different paths that you could follow. And classical physics is described by the particle, the classical particle follows the path that is described by the extrema of the action, right? So how does this story change in the case of field theory? In the case of field theory, the story changes this way, that you have some time slice Ti of space time, right? So here is just space, and this hypersurface little space. So this is Ti. Now you're gonna have your R3 at Ti here. And if you recall, we put boundary conditions. Qi was Qi of Ti was some Q initial. Same here, right? Qf of Tf was some Qf, some fixed. We fix those ones. Here we're gonna do a similar thing. We're gonna fix phi I of x and Ti. Phi I. Actually, I don't want phi. I just have one scale here. This to be, let me call it phi I. This is my Tf. We're going to have phi of x and Tf to be phi of f, right? That's an analogy. Now, I'm no longer talking about path. I'm talking about field configurations in between these two, right? Functions that live on this time interval, right? These are my configurations. To each of them, I can't draw them like that because it's no longer path. To each of them, I'm going to associate a number, a real number. The association is through the action principle, right? And that association is local, right? And then we're going to calculate the extrema. So is the analogy clear? Well, it's a generalization. Good. All right. So here's the action. We're going to vary the action. To find the extrema, we're going to take derivatives. But here's functional derivatives, right? We did that quickly at the end of the last lecture. We're going to vary s of phi. That's s of phi plus delta phi minus s of phi that we wrote this way, right? Integral of, because it's local. Okay. That is incorrect. Lagrangian density. Because it's local, the variation just comes in, right? Of the Lagrangian density. We worked that out last time as an example of how to manipulate functional derivatives. All right, so now Lagrangian density, recall, as a function. What was it a function of? Lagrangian density was a function of phi's and del mu of phi's. This includes del t of phi and del I of phi's, right? So when I do a variation, previously all I had to do was delta q of I. Now I can have variations of in space of the field as a function of space time, right? So when I do a variation, I'm gonna take a derivative with respect to del phi I, and I'm gonna take a derivative with respect to del mu phi, right? Because that's another variable. Similarly to what we did before, right? So here are the two terms. Now, with this term, I'm going to use a trick like integration by parts, right? So I'm going to write down this term as del mu of the whole thing minus del mu acting on this term, right? So basically, I'm writing this term as these two terms. It's just integration by parts. However, the catch, there's something subtle going on. It won't matter for even if you sloppy with it for the type of Lagrangians we work with here, it won't matter. But for fancier theory, it would matter. If you do, I think it is a homework problem. I'm not sure. Doing the integration by parts for the case of functionals, right, is a little bit tricky. You learn that what happens here. So here you might have been tempted to write del mu. Actually, I think Peskin Schroeder writes del mu, not d mu. But what this is a total functional derivative. So it actually has del mu of L, del mu of phi A, del L phi A, so on and so forth. So it's the whole thing. This is another example. So I encourage you as a homework problem to, even if it's not in the homework, to work out integration by parts for functionals. You're going to learn a lesson. It's tricky. And then the suggestion is to do it if you find yourself confused, do the trick of discretization that I talked about last time. If you have a function worth of things, think of it as discretize the function and think of it as many, many, many variables. Then you should be able to handle it, right? Good. All right. So what we did before was that we found this term. Now, because this is del mu, an integral of d dx mu, what does this become? What is the result of this integral? It's a boundary term. It's a boundary term that you set to zero, but it shows a boundary conditions, right? Because it's a total derivative, right? So it becomes the following object. It becomes del phi of x del mu phi of x, right? Evaluated at ti and tf, right? This is analogous to the symplectic one form I talked about last time in classical physics. That doesn't say anything more. That's a boundary term. That, for example, a simple way of setting this boundary condition to zero is Dirichlet boundary condition. Right? Dirichlet boundary condition will set this to zero. Yes.
Just for me to be saying. So in the both term, in the boundary term, you have del mu of the boundary term, and then it looks like a contraction on the index mu. Yes.
You're asking what is the where are the indices going? Yeah, I've been let me write it a covariant way. That's a very, very good complaint. Sorry, I was kind of sloppy there. Here's the right way of writing it down as this. Even mu, del mu of whatever happened. Right?
Okay. Yeah.
And because I had my boundaries in time, the only thing that matters would be time derivatives.
Yeah. Okay.
Yeah. Sorry, I think there might be wait a second. Sorry, am I something silly?
Things that the derivative of the Lagrangian with respect to.
No, actually, no. Wait.
If you have
No, that's fine. That's fine. Yeah, no, I think it's worth that actually. No. Well, that's just fine. The indices are contract.
Yeah, but then you
just
integrate and you're left with a vector quantity, right? Because you get the boundary term, and the boundary term has an index.
Right. Let's see.
I mean, it doesn't matter. It's just.
Well, yeah, it all came from the fact that up there I was kind of sloppy. Okay. When I wrote the initial variation here, right, I was a little bit casual with that variation.
Okay.
Yeah. I mean, I should have used a full covariant language of these ket vectors, right?
Okay.
Yeah. But the punchline is that the equations of motion are the Euler-Lagrange equations because this term goes away. Now you have a bulk term, right? A bulk term here that should multiply by any variation, integrate to 0. That means that the kernel should vanish, right? It means that this term should vanish. And those are the Euler-Lagrange equations. Good? All right. So in the remainder, now we're at the end of the last lecture. In the remainder of this lecture, we're going to talk about 4 examples. Hopefully we'll have time. Let's start with massive relativistic scalar field. Recall the definition of a scalar field. What is a scalar field? It's a field that when you apply a Lorentz transformation, only the point changes. So phi prime is under Lorentz transformation or Poincare transformation. Phi of x mu should go to phi prime of x prime mu in general, but it's a scalar field if this is. Right? What are the Poincare transformations? Here they are. These are the translations. These are rotations and boosts. Hopefully recall the convention. And eta mu nu is just up, is just the inverse metric. Good. All right. So here's an action I'm going to take. I claim that, well, first question, is this Poincare invariant? Is the action Poincare invariant? The action itself is a scalar. That's important, right? Now, if you have a scalar field and you want to construct scalar terms in the Lagrangian density, how would you do it? You would take phi to different powers. That remains a scalar, right? So that's what I'm doing. You could write half m squared phi squared plus v of phi. That's still a scalar. We're going to take the approximation of Gaussian field. So that's the only term I can write down, minus half m squared phi squared, right? And then what we're going to do is we could take derivatives of the field. If I introduce a derivative, that instantly becomes a vector. I have to contract the indices, and the way to contract them would be this way. This is the most general action you could write down with the following properties. Gaussian in the field, second order in the field, second order in derivatives, right? And Poincare invariant. Remember these rules. Second order in the field, second order in derivatives, Poincare invariant. Long time ago, this is a story that predates quantum field theory. Landau taught us that you go to a lab, you have this really complicated system, billions of Avogadro number of atoms. You have no idea what this is. You want to describe it. He said, you want to write down an effective action, some action that describes these degrees of freedom, right? You have a coarse-grained degrees of freedom. What are the rules to write down? Start by writing down in an expansion into the order of the fields. So first of all, identify the symmetries. You identify the symmetries, you pick fields as representations of the symmetry. That's rule 1. write down any terms that is allowed by the symmetry. I can write down any Lorentz invariant term there, concurrent invariant term, right? But then he says, if you're doing that, do it order by order in field expansion and derivative expansion. The simplest thing I can write down is a constant, a zeroth order. That has no physics, right? What does that change actually? Anyone? What does that change? Ground state energy, and quantum field theory does not care about that. It's not an observable. You could add a term phi. Why don't we add a term phi?
Symmetry.
What was symmetry?
The phi to minus phi symmetry.
You could have you might have a Z2 symmetry, phi going to minus phi, but even if you don't have that, it's not a great term to add. I'll leave it to you guys. Think about the equations of motion. You should be right.
There are constant force related to something like that.
Yeah, well, yeah. Okay, so you figure it out. Another thing you could do is you could add one derivative. Right? Can you add one derivative? No, because you cannot make a Lorentz there. So you have to add an even number of derivatives. And in terms of derivative expansion, that's the simplest thing to write down. So this is not something that I pulled out of the box. This is the thing I can write down that is consistent with symmetries, lowest orders in phi, that's non-trivial, and lowest order in derivatives. These are the rules of the game. Field theory, these are the rules of the game. You expand, and this was what we learned from Landau in like early 20s. Actually, it's right now early 20s, but 100 years ago. You expand in the derivatives and expand in the field. All right. So if you do some sort of if you separate time and space, you could write this down as in flat space as half of phi dot squared that you identify as kinetic energy density minus half of the gradient of the field phi squared. Hopefully you understand that this is just dots, right? Minus V of phi, right? That I'm taking to be Gaussian here. This is the structure. Right? Any questions about the? So right now you should be able to, if I come to you and say, I want a field theory, right? Where here is a symmetry of it. I don't know. The symmetry is something silly. SOMN or OMN. You recall what this group was, right? It's the set of transformations that preserve the metric with m plus 1 then n minus 1, right? So you look at you somehow have to study representation theory of it, and field, that just means that you write down fields with a bunch of indices that transform nicely under these transformations, right? That will tell you all sorts of different theories you could have. Then you start writing down an action order by order in your field and derivatives. That's the rule. That is the rule. Of course, you write down local expressions. Notice that if I didn't say the word local, there's nothing I can say, right? There are gazillion different ways of writing things if it's not local. Lagrangian density is a function of a point. Well, it's a function, yeah. Depends on the value of the field and its derivatives at the point. All right, good. So now let's calculate the Euler-Lagrange equations. Here are the Euler-Lagrange equations. So you take derivatives back to phi, you get minus phi squared m squared phi of x. You take derivatives here, you get eta mu nu del nu phi of x. You get two of them. You can figure that out. You add these two terms, you end up with this. By the way, I should always give you this little caveat. I will try to be consistent, but a million times throughout the course, I might switch my convention of the metric. And I apologize that in advance, because I'll try to be consistent. So you end up with this equation of the motion, right? What is this equation of motion? It says the D'Alembertian, right, which is del squared of t minus Nabla squared acting on phi plus m squared acting on phi is 0. This has a name. It's called the Klein-Gordon equation. The Klein-Gordon equation is the simplest equation of motion that for relativistic field theory. It can't be simpler than this and be dynamical, right? Yeah.
Just to clarify, can you once more say how the total derivative given there and with puzzled about it?
Total derivative
in the Lagrange equation. The partial derivative makes sense to me. I'm confused a bit about the total.
Oh, this is for you're talking about this integration by parts. Yes. You have to do the integration by parts. It's tricky. It's tricky. I'm not gonna do it on the board. I think even Peskin maybe Peskin does it properly. Maybe Peskin, but I encourage you not to look at it. Okay. Do it yourself. If you want to learn, do it yourself. All right, sorry. Yeah, this is where I was. So this is the Klein-Gordon equation, right? Any questions?
Additional terms in the field will be self-interaction. Additional terms in derivatives possible.
Anyone? Oh, wait.
Hat derivative terms, yeah. There will be Ostrogelsky instabilities.
There will be in general instabilities.
Yes.
And sorry, let me answer it differently. You will struggle to arrange generically for higher derivative terms and preserve causality. I'm not talking about causality. So what is causality? Let me give you a high-level discussion of causality. Causality is locality in time, right? It's a little bit high level, but it's complicated. In classical physics, that's it. Classical physics is locality in time. In quantum physics, there are many layers of causality if we get there. But yeah, that's right. So the instabilities that were mentioned have to do with causality. However, sorry, I apologize. I have to say this, that it's not hard to write down. So what is the issue? The issue with causality, actually, put aside causality. Did I discuss this? The number of time derivatives? No, I didn't. That's something. I didn't. So the issue is not the number of spatial derivatives. Number of spatial derivatives means more and more momentum. The issue is with the number of time derivatives. If you have taken a course in partial differential equations, you know the following fact, that if you want to have well-posed equations of motion, second-order equations are awesome. Second-order equations have very well-posed, they're well-posed and they're nice. I give you the field configuration and the first time derivative, you integrate them. You know that the equations exist, the solutions exist, and they are unique. The moment you introduce more than 2 time derivatives, things can go horribly wrong. And in general, they will go horribly wrong. So from this point of view, time evolution is kind of ill-posed. In a sense, what is at stake is the Hamiltonian picture at stake, right? There are many, many manifestations of this. Some manifestations of it in causality, sometimes it manifests in all sorts of different ways, right? But I'm going to tangent now. If I have the field, and if I need the field, the first derivative of the field, that's okay. If I need the second derivative of the field, that's like if I discretize time, the first derivative means just the difference between phi of t plus epsilon minus phi. If I need the second derivative, it's becoming a little bit more non-local in time. If I need a third derivative, it's becoming a little bit more non-local in time, right? The first derivative is tolerated. It's all good. Poincare invariance, Lorentz symmetry tells you that, roughly speaking, you should write down terms that if they are higher order in spatial derivatives, there will be higher order in time derivatives, and that's awful. Having said that, that's not necessarily true. There are theories that look, they have harder, and at the first look, they look like they're higher derivatives and ugly or sick, but they turn out to be secretly fine. Well, we'll get, maybe we'll not. It's not like you're everything. But yeah. Any other questions? In general, the rule of thumb is this. If you add a finite number of higher derivative terms, everything hell breaks loose. It's pretty bad. The only way to perhaps have something consistent, they often involve infinite number of terms. All right, any questions? Was this clear? I'm not sure. Good. So we're going to try to solve the equations, the motion of Klein-Gordon equation. You know where this is going, right? If this is your equation of motion, Fourier transform. That's your master trick. By the way, based on what I just told you, you should be a little bit of suspicious of one-time derivative as well. Where does that appear? Besides my next example, Schrodinger equation. Besides my next example, yeah. So I'll get there. All right, so Fourier transform. You Fourier transform your field in space and time. So you're gonna have maybe a 4 vector or like d plus 1 vector for momentum, or you could call that k0 as omega and vector k, right? Written this way, after Fourier transform, for the Fourier transform field, the Klein-Gordon equation is just an algebraic equation, right? That is trivial to solve, right? So what is the solution? Omega squared has to satisfy the following relation. It has to be k squared. As you can tell, I've already messed up my signs. K squared plus m squared, right? This is the so-called unshell condition. It tells you the physics of this is dispersion relation, right? The solutions are the waves. So what does the dispersion relation tell you? Recall, it was about how much energy a momentum node carries. That was the dispersion relation was. If you took derivatives of omega with respect to k, what do you find? Group velocity. And here is 1, speed of light. So this is the unshell condition. If you set m equals 0, like in a photon, for example, omega and k will be proportional, right? That's the dispersion for massless field. That's the case you probably remember from, maybe you remember from electromagnetism, or maybe some basic quantum course you've taken. E is h bar omega k and P is h bar k. So clearly energy and momentum are, well, sorry, no, I did not say that. I don't have a comment about massless fields for now. All right, that's good. What you have to have, sorry, I think I switched. Do I want to make this comment? Yeah, let me not make this comment. What I'm going to say is the following. If you look at the equation, this dispersion relation, the dispersion relation is for a d plus 1 dimensional vector, right? It has 2 sets of solution. One of them is positive frequency. The other one is negative frequency, right? This is the plot. If these are k's, you have the positive energy hyperboloid. The other one is the negative energy hyperboloid, right? Hyperboloid, is that what it's called? Yeah. Right? It looks like an innocent assumption, but one other important principle of field theory is pick the positive.
Right hand.
Yeah. Those are the physical theories. Like, you didn't have to write down something that was Lorentz invariance, but those are the physical theories.
But the negative frequency doesn't have interpretation.
It does. We'll get it. That's, I was trying to actually give you an interpretation, and I feel it's like we're running out of time enough to elaborate on that for a long time. We'll get it. We'll spend so much time on positive energy. All right. Yeah, I think last time I recall that when I ran this argument, it was ambitious and I ran out of time. That's why I'm not sure. Now, if you add interactions to your Gaussian theory. Oh, by the way, what is nice about Gaussian theory is that here's the equations of motion, right? the equations of motion of the Gaussian theory are linear. That is the best thing that can happen to a physicist. Why? Because you have a linear vector space. You could add solutions. You could define an inner product for them. You could do linear algebra. You're a teeny tiny bit step away from quantum mechanics. That's it. Once things are nonlinear, it's awful, it's complicated, right? But here, it's pretty obvious, right? If a solution is a wave going this way, you have another solution, a wave going that way, adding the two is our solution. And not only that, but all solutions are like this. The system is linear, it's not interactive, it's nice. This is as nice as it gets. Life is usually not this nice. Good? What do we do when the systems get nonlinear? Well, we could just do a bunch of Feynman diagram, get a grade, and just move on with your life. But what people will actually have to solve these equations is they usually do some sort of approximation, small lambda perturbation, and solve equations order by order, right? That's the idea of perturbation theory. But in general, when lambda is large, or the interactions are large, is pretty darn bad. You don't really have a linear vector space. You don't know how to make sense of things. You had the question before? The answer?
No.
Good. Yeah.
What is that first word before solutions? Something solutions that's small lambda.
Perturb solutions that's small lambda. P-E-R-T. I sometimes have a hard time reading my own handwriting. All right. So any questions about this? So this is all I wanted to say for, these are examples, right? I'm not teaching Klein-Gordon theory yet, but these are motivating examples. Actually, I'm sort of teaching it, but. So what is nice about Gaussians is that they're linear. Also, does anyone know why Gaussians are relevant for field theory? There's a deeply physical or even like profound science answer to this. Why are we starting field theory with Gaussian terms first?
You can get all the correlation functions out of that.
Sure, but what do Gaussians have to do with nature? What in nature, what phenomenon in nature tells you that Gaussian probability distribution or Gaussian things are natural? Classical things, think simple. There is a very deep result. Central limit theorem, exactly. Central limit theorem. It comes from the thermodynamic limit. It comes from the continuum limit. Take a variable. Let's say this is classical, right? This variable is a random variable. It has some probability distribution. P1, like say 4, you can take 4 values, P1 to P4. The next one is an independent degree of freedom. You can take a bunch of other variables. Next one is an independent degree of freedom, so on and so forth. Now, if you average all of these variables, the average is well described by Gaussian, no matter what the individuals were. This is that low energy limit, continuum limit, right? That's why Gaussians are a good start. Central limit here, that's beautiful. This is the core idea. If you don't know a probability, there are all sorts of different ways of describing this. How many of us have heard of Jane's entropy? Know what it is? Okay, there is a statistical way of statmic way of thinking about it in terms of Jane's principle. But anyway, I should stop with the tangents. Non-relativistic complex free boson is the next example. Now, what we're doing in the non-relativistic case is we'll let go of the Lorentz group, Poincaré group. What do we have? Actually, I would be impressed if you told me what the group is for classical physics. No, but like, what's the name of it? Schrödinger group. That's a very weird name. Okay, so in relativity is del mu phi, del mu phi. In non-relativistic setups, what we want is something like phi del t phi and del bar of phi squared. This is to ensure that there is rotation invariance. This will have time translation invariance, but there are no relations between time and space a priori. Right? So it's natural for me to include the lower order. Right? The rules of the game was include the lowest orders that are allowed. Rotation symmetry does not allow me to just write one del phi. That's nonsense. Right? So I have to write del phi squared. But if I don't have Lorentz symmetry, I can write phi del t phi. Nothing stops me from doing that. I'm going to take that view. It's Gaussian, it's fine, this is healthy. So that's not relativistic. Can you see already why this is not relativistic? Well, this is your Lagrangian. You could find the equations of motion. They're trivial to find. It's del t plus that nabla squared acting on phi as 0. In Fourier space, it becomes omega minus k squared acting on phi is 0. So what is your dispersion? Your dispersion is omega is proportional to k squared. That should be familiar from classical physics, right? Energy is p squared. So non-relativistic doesn't mean anything that is not here is used in the sense that not anything that's not relativistic, but it means this dispersion. Notice that everything is still Gaussian in the field. This term was forbidden by Lorentz symmetry, but I broke Lorentz symmetry. I just left the Lorentz symmetry and I'm allowed to use it. Good. Now, allow me to play. So this should be okay. Are there any questions about this? Is that clear? Now I'm gonna play a trick. So some of these at this point, relativistic field theory, relativistic quantum mechanics is kind of ill and sick. So some of these tricks that I'm gonna play here might seem ad hoc to you, but eventually it will all make sense once you view everything in terms of field theory. So another thing I could do is I could take two scalar fields, phi 1 and phi 2. And I'm just going to add them up and construct a complex vector field. Or if you want, I can think of it as a two-dimensional vector. Good? So what is the action I'm going to write here for these two scalar fields? If I want the two scalar fields to not talk to each other, so my action is like has phi 1, plus things that are phi 2, this is the action I would write. What if I actually have phi 1, phi 2? Anyone? Can I get rid of that term by field redefinition? Well, I just told you the answer. Yes, we can get rid of it by field redefinition. All right. So here's the action I've written. I over 2 phi star del t of phi minus del t of phi star phi. This is real. You could check that. Just expand it. Not only it's real, but it's also a familiar expression. If you expand it, you'll see. Sorry? It's like phi 1 terms plus phi 2 terms. Yeah. There's no I. Like once you expand it in terms of phi 1 and phi 2, there are no i's in there at all. And then this is the kinetic term. Now, something funky happened. What happened was that previously we were putting phi squared next to this term. We're adding these two terms, right? The coefficient of this was minus half. Now, dimensional analysis tells you that every time you have del mu, that's 1 unit of mass, right? So when you have del mu, 2 del mu's, that's 2 units of mass. So this is mass squared. Now what I'm adding is phi del t phi to this. Sorry, I'm adding phi del t phi plus what was I adding? Oh, this term. This is this term. There has to be a coefficient that's it, right? That's dimension 4. That coefficient, it should have units of inverse mass. it has to have units of length, right? Because in one case you have two derivatives, in the other case you have one derivative. If you have ever taken any field theory in the past, you should be very, very concerned. If you see anything like that, you should be very concerned. Well, we'll say that many, many times until the end of the course, why that's concerning. All right, but let's say you don't know anything about that and we just push through. So the Euler-Lagrange equations are what they are. You just plug them in. The derivative with respect to phi star and phi. Notice that phi and phi star are now independent degrees of freedom. So I have to actually a pair of equations, or a pair of Euler-Lagrange equations. You write them down. This is the equation of motion you get. Delta I del T of phi minus A over 2 Laplacian of phi. This equation looks awfully like Schrodinger equation for a single free particle. And the interpretation of this A would be the inverse mass of the particle. If A were 1 over m of this particle, we would have a nice match. But the comparison is kind of crazy. It's apples and oranges. I'm talking about a scalar, classical scalar, non-relativistic theory. Equations of motion of it. There's no quantum mechanics in here. There's no h bar in here. The other equation is Schrodinger equation. Has an h bar, but that's set to 1. Where is the h bar, by the way?
1.
Yeah. Sorry. What was the answer? Where's the h bar? No. Well, where would the h bar be? I'm hiding it. I've set it to 1, but I'm hiding it how? Does anyone know? I've said this before. What is the dimensionality of action? It's h bar. So I'm not really allowed to just like freely put it. I'm not allowed to exponentiate it or freely play around with it, right? So when I say action, I really mean 1 over h bar action. Because, when we talk about in the action, when we talk about, we want to compare actions. One is larger, one is smaller. That is only fair if these are dimensionless numbers. So there's 1 over h bar somewhere. In classical physics, there's another scale. All right, so that's what it is. So it looks on the surface similar, but these are very different. In one case, you have a classical complex field. The other case, in the one case, phi is a classical complex field. In the other case, it's a wave function. The solutions of both cases, Schrodinger equation and a classical field for a complex scalar field, non-relativistic, are both these plane waves with the same dispersion relation. So it means that there is a one-to-one map between the space of solution to equations of motions. This is a classical phase space of a complex scalar field that's non-relativistic, and the Hilbert space of a single quantum particle. What is a Hilbert space? It's a complete linear vector space that there's one more. Right?
Defines color.
There's an inner product and a closed respect to inner product. I need an inner product to make the comparison fair, right? What is my inner product in this case? Sorry? It's
the integration of
well, I'll let you guys figure it out. I can give you a tip. It's induced by the volume of the phase space. It's a good exercise to play with this. All right. Is this a coincidence? Is there something deeper in it? But let me repeat. There's a connection between the space of the classes until when? Oh yeah. There's a one-to-one correspondence between solutions of classical equations of motion complex scalar field that I said, because it's a linear solution, the set of solutions from a linear vector space, I can introduce an inner product, so I can build a Hilbert space. I don't know how familiar you are with this, but this is a Hilbert space for classical, right? I can do that. Nothing stops me from doing that. And there's a natural inner product for it, given to you by the phase space, the volume of the phase space. And basically, that problem maps very nicely the Hilbert space of a single quantum particle. For now, just leave it as it's an enigma. It's a problem, or it's like some surprising connection, unless you already see where this is going. We'll demystify this. It's not all that, well, it is interesting, but this is to be taken seriously. This is not a random connection. Does anyone know actually what I'm getting at? Okay. All right, so that was example 2. Example 3 is Maxwell theory, electrodynamics. So this is an odd example, weird example, because so far I've been insisting on locality. I've been insisting on locality a lot. This theory is non-local. It's something we look around in nature, we see these theories, and all of them, most of them are local, except for some of them. They're not non-local in like as in a wacky sense that the action is like has a billion intervals in time or space. They're actually almost local, modulo some subtlety. They're they have a special form of non-locality. So these theories, I'm going to describe them in a bit. What they are, they have local degrees of freedom. So they are local, but they have one extra set of non-local observables, and they are related to topology. We'll actually get there, maybe. But they have a very, very special form of non-locality, right? It's not a crazy new theory. It's called electromagnetism. So you've seen it before. So what are the degrees of freedom? The observables. By the way, when I say observables, also I mean classical physics as well, right? What are the observables of classical physics? Single particle.
Position and momentum.
Position and moment. Well, those are observables, but what is the general observable? Any measurable function in the phase space. Any function of x and p. Of course, if x and p are measurable, observables, right? And the term measurable because there's a volume on the phase space, blah, blah, blah. But yeah, that's right. All right. So here, electric field and magnetic field are the observables. And you have charge density and current density. And Maxwell taught us about these 4 beautiful equations. What's the Lagrangian density of this? The Lagrangian density of this theory is indeed local. It's half E squared minus B squared. So even though the theory has non-locality, there's a Lagrangian density that's local that gives it. But there's a little bit of a problem. This Lagrangian density does not look like the form we're familiar with. It doesn't have time derivatives in it. It doesn't have space derivatives in it. It's weird.
But it does. I mean,
no, it doesn't.
Do something like that. If you write it in terms of the 4 potential.
What is a 4 potential? I don't observe it.
Yeah.
That's exactly the trick. The point is, what we observe is our E and B. 4 potential is a made up. It's literally made up. It's some made up construction for us, so that we could write it in terms of del T and del bar and have a local view. This is really the origin. This is really the origin, right? So the theory looks like it has a Lagrangian density that's local, but it is essential. I haven't explained this yet. There are many layers of it's like locality is low term. But for local theory, you like this structure. And we don't have it. So let's make up some imaginary degrees of freedom, right? Package them in terms of this vector potential, right? So basically, you can see these 2 equations precisely do the job, right? I'm turning E and B into time derivatives and some spatial derivatives. I have to write Carol or things like that because these are forms, differential forms, blah, blah, blah. There's an elegant way of seeing all of that. I might actually go over it in a bit. The point is the vector potential and the gauge potential. Sorry, what's that called? Phi is the electric potential. Electric potential, they are made up. They have redundancies. They are unphysical, right? What are the redundancies? If you take your scalar potential, sorry, your vector potential and your I guess Coulomb potential, what is that called? I don't remember. Phi, and shift them by a derivative and derivative of an arbitrary function, nothing in physics changes. So you fix the problem. The theory was on the face of it non-local. You introduce some imaginary stuff, right? Some extra redundant degrees of freedom, forced it to become local, right? So what is the cost you've paid? So let me zoom out. What you do is that this theory was non-local, but we wrote it as a local theory with an extra constraint. The constraint is like, for example, Gauss's law. Not every A and phi are not dynamical fields. We're going to see that in a second. They can't take arbitrary values. They have to satisfy Gauss's law, right? Those are constraints, and those are reflections of the fact that the theory was non-local. But it has to do with the fact that there's a very, very special form of non-locality here that has to do with topology. Yeah.
But quantum mechanics infinite space. When I write an quantum mechanics,
that's the niche of topology. Yeah, that's the niche of topology. It's not that A and phi that matter. It's the monodromy of them that matter. Monodromy. As you go A and phi, as you go around the loop, the non-contractible loop, that is an observable. So Wilson line. So you take the last course. It's the Wilson loop that's an observable. That's non-local, not A. A is never observable because you could, like it's a. Well, we'll talk about all this. It's topology. I'll actually describe what I mean by topology. This case is so easy that you could explain it. There's no physics associated to alpha. So what are the physical degrees of freedom? The physical degrees of freedom of E and B. How do you write down E and B elegantly in terms of this made up A mu and A mu? By constructing that object called field strength. Del mu of A mu minus del mu of A mu. It has two Lorentz indices. It's a tensor, right? Actually, it's a 0 to 10, 4. It's a 2-4, for those of you guys who know what forms are. It's gauge invariant. Has no redundancy. Later on, you will learn that this is a coincidence in electromagnetism, and there are some cousins of electromagnetism where the would-be field strength is not gauge invariant. Like as soon as the gauge group is not a billion, it will not be gauge invariant. All right, so here they are. F0i. So this is an anti-symmetric tensor. Should be obvious. Right? On the diagonal is zeros, and the 0i components are electric field, and the space components are magnetic field. All right, let's go back to the Maxwell equation and write them elegantly. Now we can think of the forecurrent as the current, the time component, which is the charge density, and J, right? The vector current. The first two equations, there were 4 Maxwell equations. The first 2 of them could be written compactly in terms of the following equation. Del mu of F mu nu is J mu. Right? Those are the first 2 equations. Ignore this for a second. So those are the first 2 equations. Now, if you take a derivative of del mu of the left-hand side, you learn that because this was anti-symmetric, this should be 0. That means that this equation implies that del mu of J mu is 0. Implies conservation of phi. charge is conserved. It's already built in. So far, so good? All right. What are the other two degrees of freedom? Oh, sorry, what are the other two equations? Equation 3 and 4 of Maxwell equations. You could write them in this way, where this is a totally anti-symmetric tensor with 4 indices. In fact, it's conventional to define this object. It's called the dual tensor. It's a field, right? It's like it's called the dual fields, right? And the equation 3 and 4 of Maxwell equations is the statement that del mu of this guy is 0. So Maxwell equation basically boil down to the statement that you have F mu nu, del mu of this is J mu. This tells you that current is conserved, right? J mu is conserved. You also have this equation. This is the dual. So what is the Lagrangian? The Lagrangian was, I wrote it, E squared minus B squared, right? Written in terms of these, oops, what's going on here? Written in terms of F mu nu, this is the Lagrangian. And I've added actually source. So the Lagrangian is just minus 1 over 4 F mu nu, F mu nu. This is gauge invariant because F mu nu was gauge invariant, right? And the indices are lower, raising and lowering of indices is through through Minkowski metric. This is just a charge, source that I add, but this term is also gauge invariant. This is super crucial. This term is gauge invariant. Why? Because the current is conserved. So let's take a step back. Nobody complained about this, but you couldn't complain about this. All along, I was saying that locality is the statement that I have a Lagrangian density that I integrate over space-time. It seemed like the Lagrangian of electromagnetism was E squared minus B squared, which is Lagrangian density. But then I insisted, oh, I wanted it to look like the time derivative of space derivative. That was not part of my description of locality, right? So what is the deal? The deal is as simple as this. You could write E squared minus B squared, but you could never source that or couple it to charges in a local way. The action of Lagrangian density of electromagnetic field is local, but it cannot be coupled to charges in a local way. That's it. There's no way of writing J mu A mu as a local term in terms of E and B's and charges. There is no way. That is manifested in the fact that you had to write in terms of derivatives. Right? So the principle is still the same thing. The action has to be an integral of a local object, local density, right? Here it happens magically because that term you added over there, it was good with Lagrangian density. So it was a density. It all looked nice. It's local, but you're running the risk of it. The fact that now you introduce this A mu, and now this term might be gauge dependent. Conservation of charge del mu J mu ensures that it's not. This is gauge independent. Do you see why it's gauge independent? Right? Just shift it. Do the gauge transformation. There's an important lesson. I sometimes push things under the rug. If you did this calculation for yourself, you could check that this gauge invariant, if you can drop some boundary terms. So that will come back and bite you later on. All right, good. So, oh, by the way, this is called the Bianchi identity. this action is again, going back to Landau's principles, it's the simplest Lorentz invariant, gauge invariant, parity and time reversal action you could write down with no more than two derivatives. Now, what is this parity and time reversal? If I relax that, can I write the next term? No. If I relax, just think of electric field and magnetic field. Is there something else that I can add to my E squared minus B squared? Another term that looks nice. But it would violate parity and time reversal. Gauge invariant is automatic because you're writing in terms of unity. So what is the action? E dot E minus B dot B. What else could you do? E dot B, right? That term is okay, but it breaks parity and time reversal, right? CP violation, exactly. But we don't have to talk like quantum language. What is this? So there was this question before. We're going to come back to this when we talk about representation theory. But is the Lorentz group this, or is the Lorentz group this? We'll see that this group has 4 disconnected pieces, and they're connected to each other using parity and time reversal, right? So it's my choice to write down the theory that on top of these local Lorentz transformation is invariant under parity or time, or not. We look at where did this come from? Nature. We go look outside. You know, like Lorentz transformations are a symmetry. Good. Let's test to see if time reversal is a symmetry. It's all good until it's not, right? So it's a question of what are the symmetries, and if you don't allow for parity time reversal, if you want parity and time reversal to be a symmetry, this is the most general action. But then, well, I'm not going to write it anymore. There's a simple way of writing E dot B here in terms of the field and the dual. That's also easy to see. But anyway. All right. Any questions? So let's take this action and vary it. What you obtain is, well, you're going to get 2 terms like the above, right? There was a reason that I put minus 1/4 in front of F mu and F mu, because there was a factor of 2 and I wanted to get minus half here, right? After an integration by parts up to boundary terms, you get del A mu, del mu F mu, and equations of motion are, not surprisingly, what I just raised. Right? So these are the equations of motion. The Bianchi identity is automatically satisfied by the virtue of the fact that I would pick the 2, 4. Bianchi identity is equation 3 and 4. All right. So now I have an extra comment. Electromagnetic duality. Let's set J mu equals 0. No currents, no charges, no currents. Just pure electromagnetic fields freely propagating in space. This theory has a symmetry. If you send electric field to magnetic field, and then magnetic field to minus electric field, this is symmetry. This is called the electromagnetic duality. Under this transformation, the field and its dual, field strength and its dual are exchanged. That's what it does. This is the symmetry that's spoiled when you allow for E dot B. The symmetry is spoiled. So in summary, so why did we introduce A mu, even though we knew it had unphysical redundancies and was made up? It's because we wanted a local description. We wanted to be able to couple the theory locally to charges. That was the only desire. This is the origin of gauge invariance. It's never a symmetry. Don't ever see these words. There's no such a thing as gauge symmetry in nature. That's a misnomer. That's incorrect old terminology. Gauge redundancies and gauge invariance. These are the only things that exist. Symmetry has to do with space transformations of the Hilbert space. Nothing. This is just made up. This is in my mind, right? There's nothing acting in the Hilbert space. It's all made up. we could not couple the electromagnetic field to current using a term that in the Lagrangian that was both local and gauge invariance. That's why we introduced AB. So we, yeah. Oh yes, there is. Yeah. Well, we'll talk about that because we haven't talked about conserved quantities. Those are another very well. Okay, so first, let me just say quickly. The connection between conserved charges and symmetries is for continuous symmetries. So Noether's theorem and Noether currents and all that is with that. But yeah, we'll get there. We'll get there and talk about it. It's basically CP.
This is not a continuous symmetry in this case.
It's what?
Is it a continuous symmetry?
No, it's not. It's not. It's just Z2. It's just Z2. Right? Space and time impaired. It's just F to minus F and F tilde are swapped. So now that we introduce this redundant degrees of freedom, we should also make sure that when we do calculations, things are good. So we usually do something called gauge fixing. Now, there is some interesting consequence of this gauge fixing. What I'm going to describe is not just a set of words, there's physics associated with it. Do I have time to go through this? Yeah, I'll probably skip the example 4, but I want to explain this well. What was the action of electromagnetism? It was F mu nu, F mu nu. If you expand this and write it in terms of A mu, it's basically this guy squared, right? So if I think of this as a 4 vector, there's something suspicious going on for A0. What is it? Can you tell?
It's derivative.
It has 0 time derivatives, right? It has 0 time derivatives. It's non-dynamical. It's a constraint, right? This is not a degree of freedom. It's fake. It's made up.
There's no conjugating moment.
Doesn't have conjugate. So A0 is a constraint. We'll see that, maybe not today, but when we get to QED or maybe earlier than that. You could literally integrate it out and just plug it into equations of motion and get rid of it. It's easy. This is easy, right? But I want to make sure that it's clear that sometimes you could pick a gauge where you call this potential, right? And then this is A. But keep in mind that this potential, electric potential, is non-dynamical. You tell me where the charges are in nature, I calculate it. I don't need to know any time derivatives whatsoever. Tell me where the charges are, I know where the electric potential is. It's Coulomb law, Gauss's law, right? There's no dynamics associated with this. It's just a constraint. Once you tell me your distribution of charges, it's fixed forever. But this is non-dynamical. It's a manifestation of the fact that we need the 2 time derivatives for dynamics, right? Whereas the other guys look like they're dynamical. So first we start with 4 degrees of freedom, seemingly. One of them is killed. One of them is not a degree of freedom, which is a constraint. It's a stupid thing we did because we insisted on locality. Now let's see if the other 3 are real. We still have to talk about gauge fixing. There are various ways to gauge fix to kill the redundancies we introduced. For example, you could pick n mu is for some 4 vector, A mu equals 0. If n mu is space-like, it's called axial gauge. If it's light-like, called light-cone gauge, and n mu is time-like, it's called temporal gauge. And why would you make such choices? Well, actually, those are some choices. Let me talk about the nicer choice, in my opinion, called Lorentz gauge. Here's your equation of del mu f mu nu. It gives you box A nu minus del mu A mu equals 0. But of course, gauge degrees of freedom here are just redundancies, right? So a convenient choice of gauge is to set del mu A mu equals 0 so that this looks like just 4 independent degrees of freedom. This is what you would have written if you had 4 scalar fields organized in a vector or something, right? You do this, it's all good. What are the solutions to these equations of motion? These are just 4 Klein-Gordon equations. So it's just Klein-Gordon waves. And then there will be a vector that there will be C of mu, which is the wave function, or not actually called wave function. It's just a function of K that I'm allowed to put there. Because if the solutions are all plane waves, I sum them with arbitrary coefficients, that's a solution, right? So those are light waves. And that C of mu has a name. It's called a polarization vector, right? But now, let's look at my gauge. Del mu of A mu has to be equal to 0. This is my A mu. If I take the derivative, it tells me that K mu and C mu have to be orthogonal in 4-dimensional space. So it's not true that I have 4 degrees of freedom C. I already killed one of them, right? So I was talking about 3. This also kills another one. You're left with 2. A photon has 2 polarization. That's a consequence of gauge symmetry. Sorry, I said not say that. Consequence of gauge invariance, right?
But that's only for massless fields, right? Because you still have spin one particles that have.
Yeah, we're talking photon. Though that would not be a gauge.
But so the gauge invariance comes from the fact that we don't have mass, right?
Gauge invariance requires you to have no mass.
Okay.
Mass would spoil it.
Okay.
All right, but not only the counting of the degrees of freedom works, right? 2 modes, but also what does this tell? Can you say in words what this says? It first says that let's think of the C. Well, hey, what does this say?
Polarization and direction of propagation is quantum.
Exactly. The photon could have polarization perpendicular to the direction of propagation, right? Now it's a 4 vector. You have a choice to trivialize the A0, which is killing the time component. Now you have a polarization vector is some vector in space, and it has a momentum. The photon is moving with some momentum. There's a 2-dimensional vector. Hypersurface perpendicular to it. Polarization is something on that. This should connect with what you know from electromagnets. Right? Sorry, we ran out of time. I'm just going to summarize and skip example 4. All right. So what did we talk about today? We talked about, I actually forgot what we started with, but we talked about 3 examples, right? Scalar field, massive free scalar field. It was a Gaussian, relativistic scalar field, Klein-Gordon equation. It was a Gaussian theory. It was a linear, it was the equation of motion were linear. We talked about plane waves as a solution and such. Then we talked about, that was a Klein-Gordon. We talked about non-relativistic complex scalar field. The action suspiciously looked like the Schrodinger equation. And I just stopped at this level without discussing any further physics, that there's a 1-to-1 correspondence between the space of solutions of the theories, and there's an inner product which we define here, there's an inner product which we define there. There's a Hilbert space on both sides that you could match in one by vector by vector. Example 3 was gauge theory. This was the very first example of a non-local theory. But it's not wacky non-local, it's local. ENB are local degrees of freedom. You haven't seen this, but it happens to have some degrees of freedom that are not local ENBs. They are non-local degrees of freedom. For those of you guys who have heard these words, it's a Wilson. They're non-local degrees of freedom, but in this formulation, it's not quite clear where they are, right? But we had an action that we've seen in nature. We couldn't couple it to charges, currents, in a local way. We insist on doing that, and we pay the price, right? We had to introduce made-up redundancies that we described and led to 2 polarization for photon instead of 4 polarization. Any last questions? Thank you so much.
So the way to write that, if you remember, is something like this.
Minus epsilon plus epsilon.
So it does both ways, but it presents this in a way that is that clear? So that was the the classical picture of dictionary, right? Why you shouldn't just turn two straights.
Yeah.
Right? Because you're basically saying in this case, right? So for example, if I had a little magnet, if I tilted a little bit on the force, right? But remember, the spin has an angular momentum. It's actually something that's spinning, right? So remember, we said that if it's a spin, if it's something that's like a if it's tilted initially, and you apply force, it keeps tilting. It just processes. So it never straightens. The angle never changes. That's the key. Yeah, it does. Yeah, exactly. So it does this, but it does so in a way that projection along the axis doesn't change. So that's why the picture you had doesn't quite explain.
And that's why it's just like it's still like doing the whole
Correct. But as long as so yeah, so the really is All of them are natural. They are actually
It's a very quick question. So during the talk, we're talking about this, that so you have your system of qubits, you have control over the individual node, like let's say if you have individual qubit, is the evolution of it described by some sort of knot equation, and you have control over the coefficients individually. How many qubits of that type do you have? Whoa. Okay, so we're debating about this.
By now, so the Lydic experiment is going
That is wonderful. That is wonderful. There are already things to look at. so-called well resonances. So this is basically the decay of the two-point function in time. Decay is exponentially fast and long time, and reading of the exponent is the coefficient of the exponent is some discussion about that. And it would be like this. I guess the idea would be to look at the dependence of it on the number of sites, the coefficient, right? And also parameters of the your Liblac.
So yeah. So in fact, so I guess it's a little bit of a question of practice and how the scaling goes. So let's say assuming 10 qubits is enough to see scaling enough.
Well, that is fine.
Yeah.
10 is more than.
But then I guess since it shows up in fact,
That is more.
right, which is more. So we actually do in our specifically, we do have some control over actually over the defacing paragraph. But we can turn it down. 0, we can turn it up. So that's one way you can do it. Of course, it's still a question of how time management be.
Like currently, without really changing your setup or anything, even perhaps even for calibration, have you looked at the two-point functions in time?
So
even a single qubit, let's say.
So how do I think about so single qubit meaning I measure single qubit. Okay, so single qubit just put it in let's say.
Oh, you have a sorry, I'm going to call it harmonic oscillator is more natural for you.
No, qubit.
Qubit.
So I guess we have finite, finite defacing. So right now, okay, I guess the thing is right now, some of the devices we have so it's the basic. So the state just doesn't. So for single qubit, I guess you're pretty much just. So when you say two-point correlation,
well, maybe I can ask the question differently. So when you, I guess maybe this is not what you meant, but how do you model the leak of information? This is a Lindblad equation, right?
Yeah.
How do you read out the Lindblad coefficients?
Yeah.
For that, you have to look at the two-point function.
Yeah, exactly.
That's literally what you have to look at.
Yeah, okay, exactly. So yeah, so exactly. So for single qubit, we just do a Ramsey experiment to get basically total.
Okay.
So yeah, okay. So this is starting with the qubit in the ground state.
Yeah.
You do a pi over 2 pulse, put it in the qubit. So this is of y.
Yeah.
And now because you have some defacing, which is sigma z.
Yeah.
So the 0 and 1 they start to rotate. So you wait a very good time. By a second pi over 2 pulse. Check.
Oh wait a second. Sorry, so you are looking at the two pulses separated in time.
Correct. So it is a 2-point.
Oh,
it's a single qubit.
Okay. Yeah. I mean, there's no other way of reading the coefficient.
Yeah.
I see. So
this is the typical measurement we do to get a total defacing. The relaxation is similar. You excite it into the excited state, the 1 state. You wait a very long time. You measure and see how much the energy is decayed. That's the energy.
yeah, okay. Question at this level. So, roughly speaking, do you model your Lindblad operators or jump operators like sigma z, sigma x, or whatever it is?
Yeah, so sigma z for the defacing in the most naive way.
Yeah.
And sigma x, sigma plus.
Actually, yeah, let's talk sigma plus of sigma. So sigma plus is emission, or vice versa. The other one is absorption, right? So to read off this set, can you read off the coefficient separately?
Yes, yes.
These are already like the details of the calculation these guys are doing.
So the way you, again, single qubit is easier because so let's say in our real experiments, the decay, the signal minus, is just the qubit decay. The plus comes from the fact that your environment is not zero temperature, so there is some thermal compensation that can keep up.
Yeah, absorption versus
exactly. So what we can do is we can actually compare. So we want to essentially compare the qubits in the computation, not in the thermal.
Yes.
The stain wouldn't be able to see the.
Yes. Yes.
So if you compare it on a computational basis, we have some resets. And then if you compare excited state, you can see how it behaves. If you're comparing the ground state,
oh, I see. So you find the way you find this in that the separate S plus and S minus by initial states.
Mm-hmm.
Right, because S minus cannot be done twice. Yeah. Okay.
In fact, I can tell you more later. We are actually doing some. So we are actually doing some of these characterizations for medical systems. So we're actually trying to. So we're actually trying to map out all of the correlated relaxation basic in this case for. So this is not intrinsic medical physics, but the environment has some structures that so you can actually see. So one example is you can see some kind of superbus as a separator. So you can see what. So superbus is separated. So some collective. So for example, you have 4 qubits there.
Yeah.
And you have a medical state that's plus.
Yeah.
Meaning phase.
Yeah.
It will decay faster than plus.
Okay, awesome. Whenever you have time, let's discuss this a little bit more. I would love to actually, whenever you have time, see quantum mechanics.
Okay, of course.
Yes.
I think we're getting closer. I haven't forgotten.
Yeah, no, it's all right.
Okay.
Thank you.
The title of the talk today is Entangled Islands. I'll drag on the Mr. as a quantum mechanics top 4, and the floor is yours.
Thanks a lot for the pressure, because I think I never got that long of an introduction before. I think really always distinguished. Thanks so much for that. So yeah, I will try and give you an introduction to the physics that we do in particle physics. Talk about what I do, which is talk about physics, and then because I never can resist it, talk about the mechanics portion. These are the few slides to give you an idea of that. Okay, so then I'll go ahead and that's what I should actually do this. So the main, let's say, the physics of the talk that I wanted to talk about, and I will get there, is exactly what is described in the title. So it's the entanglement of particles. And for the first time, or actually the second time, you will see a result here in this talk. It was carried out and done at the Large Hadron Collider. Usually these kind of experiments are done at very low energy scales. And now we have been able at Atlas and at CMS, that's our competitor experiment, to do these measurements at very large energy scales, at the TeV scale. So I get you hopefully there and explain what that all means. So, okay, some of you hopefully, or many of you will be familiar with the standard model. So this is the standard model of particle physics. We have our building blocks of matter, we have quarks. These are separated, well, put into generations of families. We have the first family, second, third. We have leptons as well, also they are split into the same order. Up and down is everything that is around you, right? The protons make the two up quarks and a down quark, electron around it, that's a hydrogen atom. So this is the easiest or the simplest atom that we have. And then we have the higher generations. Those are all not stable, so they will eventually decay. The one that I focus on at least since 15 years, before that, as Gabor was mentioning, my PhD, so that was focused on the charge. So I moved up in mass from the second generation now to the third, and most heavy fundamental particle that has been discovered so far. All of these particles then take part in interactions. Those are mediated, at least the best we can tell. Currently, the best model that we have is by gauge bosons. So we have electroweak bosons, C and W. Those are for electroweak decays, radioactive decays, decay of the neutron, for example. We have the photon, that's our light electromagnetic interactions. Chemistry. The gluon then is